Today, our main topic is something called the chain rule, which is essentially the rule that you will apply every time you take a derivative. So let me start with a really simple example to kind of illustrate what it is we're going to do. I would like, let's consider y is, I'll do something fairly small. Y is 4x cubed minus 2, and we're going to square it. Okay, I want to find dy dx. Well, it seems reasonable because if I'm differentiating x squared, I would just say 2, boom. So it seems reasonable that my answer should probably look something like this, because off to the side, if I had differentiated a variable squared, we know the answer is just 2 times the variable. So now I'm differentiating a function squared. So it seems reasonable, 2 times the function. I mean, that's a good starting point. How do I know if this is correct or not? Well, let me go back to y and let me actually square this out. All right, let's go ahead and multiply that out. I'm squaring a binomial. So it'd be the first term squared, and then 2 times first times last, and then the last term squared. Okay. So y is equal to this. I only picked a 2, so it wouldn't be terrible algebra. Now, I know this is y, so I know then dy dx is the derivative of this. So this would be 96x to the 5th minus 48x squared. Okay, I have absolute certainty this is the derivative. And you know what? These are not equal. So this can't be the right approach. Or it might be the right approach, but I'm just not finished. Let's go back to here and let's see if we can factor this, all right? Can I factor anything out of this? Well, I think I can factor out a 48 and an x squared. And that would leave me with, what would that leave me with? 2x to the 3rd power minus 1. Well, that's not exactly what I want. These are really close together. You know, let's do this. Let's throw another 2 back into here. Let me write it like this. 4x cubed minus 2. And then I'd only have half of that, okay? Sorry. I'd have 24x squared left over. But I'm going to put 2 of it right here and the other 12x squared over here. Now do a quick check. If I multiply this out, I will in fact get this, which will give me this. Okay. Now this is a goofy way. This, by the way, if I said what's the answer, well, obviously I'd pick one of these 2 versions, but I'm kind of taking it to the, those answers do kind of resemble each other, don't they? Except the second answer has an extra piece. It has that piece. Now, what is that piece? Where did that piece come from? Well, let's go back to the original problem. 12x squared. Hey, isn't 12x squared exactly the derivative of this? In other words, if I said, I want you to differentiate this, then I would have a 12x squared. And then I would have my correct derivative. So the key was I did do this to the 1st power, but then I followed by taking the derivative of this. This is what the chain rule is. So I'm going to say it in a formal sense, and then we're going to do about a bazillion examples. The chain rule is how you differentiate not x to a power, but function to a power. It's not how you differentiate the sign of x, it's how you differentiate sign of a function of x. In other words, it's how you differentiate a composition of functions. So if y equals f of g of x, that's called a composition of functions. So in this last example, my g of x would have been the 4x cubed minus 2, and then f was squaring it. Then dy dx is f prime of g of x times g prime of x. And that second piece we generally refer to this piece right here as the chain rule factor. If I make a mistake, it's probably going to be that guy right there. I might forget him or something like that. So it doesn't matter what function it is. I differentiate it like it's just an f of x, but you notice that this didn't change. G of x is called the argument. In any problem, the argument cannot change. Okay, so in my final answer, 4x cubed minus 2 was the argument. That was the thing I was raising to a power, and it showed up in my answer. Okay, so let's do another version of this. Let's do another simple exponent problem. So I want to differentiate, let's say I have 6x cubed minus 10x squared plus 3, and I'm raising that to the 10th power. All right, let's have some fun. And I want to differentiate that. Well, there's two ways I can do this. I can multiply this out. You know, that'll take me a little while. Differentiate that and then refactor it. And that might take me, well, you know, the rest of the day. That's probably a bad idea. Or I look at this and say, I have function raised to power. So my derivative is 10 function raised to the 9th power, right? Brought this down, decreased by 1, but at some point I have to deal with this. This part right here, that's that. I did f prime of the big picture, but now I got to do the derivative of the inside piece. That's the g, because that I'm calling the g. So times the derivative of 6x cubed minus 10x squared plus 3. So the best answer I can give is going to look like this: 10 6x cubed minus 10x squared plus 3 times 18x squared minus 20x. Now, can I keep going? Well, do I have a common factor here? Yeah, I have a factor of 2. 2 is not the issue. It's the fact that I have a factor of x. So I can factor a 2x out of that statement. And that would then, the best answer I can give then would look like this. Sorry, this is getting a little bit tight. So that 9th power on there still. And then what's left here would be 9x minus 10. The order of the factors isn't what's important. It's the fact that I have it. In fact, okay, mute yourself, guys. Please mute yourself. That's really loud. It's in a factored form. The first and most important application of any derivative, as we will see, is where does the derivative equal 0? And I'll give you a simple rationale for that. If I was drawing a graph, you know, and the graph is turning around and, you know, I have all sorts of interesting stuff going on, where does the graph turn around? Well, the graph will generally turn around exactly where you have a horizontal tangent line. And where do you have a horizontal tangent line? Exactly where the derivative is 0. So in order to figure out where a graph turns around, I'd have to know where the derivative equals 0, which means I need my derivative in a factored form. So whatever the graph of this looks like, I can tell you it's going to have horizontal tangents when x is 0 and when x is 10/9. Now, I don't know about that part, but I have identified a couple of simple spots right off the bat because I have it in a factored form. Now, let's keep going. Are there common errors? Yes. I hate indicating errors because when people, when you take notes and you write down an error, even though it's intentional, you write down an error in your notes and then maybe later say, you know, don't do this. Once it makes it to your notes, it's the law. And if you put an error in your notes, usually that means that's the way you're going to do it. And I always love it when people say, well, I put it in there and textbooks do this. Don't do this. And sort of like in Shrek, in the first movie, when him and Donkey are on the bridge and you know, Donkey's like, don't do that. Well, what's the last 2/3 of don't do that? Do that. So when you say don't do this, you hear the do this and you do this. Never write down errors, even if you're saying don't do this. Here is the only universal error. This is the universal error right here. This is an error because I changed the argument. In other words, I made the argument my chain rule factor. I don't want you to write this down. This would be basically me doing something like this. I've got 3x squared minus 4 to the 5th power. I'm going to keep it simple. I know the answer is 5 quantity to the 4th times derivative of quantity. But the mistake that I will see people do is right there. I replaced my argument with the chain rule factor. Now there's nothing else to write. Well, obviously these are not the same, but it's an easy error to make if I'm not paying attention. The reason I know it's an error is those are not the same thing. They have to be the same thing. An argument cannot change. Am I going to take the derivative of the argument at some point? Yes, that's called the chain rule factor. And it's a chain rule factor, which means it's at the end multiplied. And that's the key there. It's being multiplied by the quantity. So how else does this chain rule thing work? So far, I've just done things to powers. Well, what if I have something like this? I would like to differentiate the sine of x cubed. Now I know how to differentiate the sine of x. The derivative of sine of x we now know is the cosine of x. So the derivative of the sine of x cubed must be the cosine of x cubed. I know that has to be the case. The argument cannot change. But at some point, I have to deal with the fact that I have an x cubed. And that's the next thing that's called, again, the chain rule factor. It's sitting right there. Now, if I take the derivative of x cubed, I'm going to get 3x squared. The question is, where do I put it? Well, typically, when you have polynomial-ish things, x's to powers, multiplied by transcendental functions, things like, sines and cosines, we typically put the x to the power in front, not because it's more correct, but because it's easier to read and probably easier to deal with. So I would put the 3x squared in front. It's just a more useful version of the answer. Now, the 3 has to go in front because it's a coefficient. A coefficient can't go anywhere except in front of the thing. But the x squared could have gone to the other side, but I think most of us agree that reads very nice. That's it. So now I said you're going to use the chain rule every time you ever take a derivative the rest of your life, if you're doing it correctly. So what if I was just doing this? What if I'm doing the derivative of the sine function? There's no chain rule there. Well, actually there is, because this is cosine of x. My argument is x. So if you will, times d dx of x. But what's the derivative of x with respect to x? That's just 1. So even if I don't have a composition of functions, even if my argument is simply the x, the chain rule factor would actually still be there. It just happens to be 1, so we don't write it. Don't do this. You don't need to ever do this, but it is absolutely correct to do this because my final answer is still going to be cos x. So you don't say chain rule factor only exists when I have a composition. Actually, chain rule factor is always there. It's just sometimes the chain rule factor is 1. And when it's 1, we don't bother writing it. It would be sort of like saying, I have a quotient, but my denominator is a 1. I don't bother writing it. I just write the numerator because it's the same thing and it's easier to deal with. Let's do a couple of these bad boys. I would like to take the derivative, let's say, of the tangent of 3x squared minus 4x. Well, that comes in last. So the first thing I'm going to do is the derivative of the tangent function is secant squared. And I like to use formal mathematical vocabulary. So I'm differentiating the tangent of thing. The derivative of the tangent of thing is the secant squared of thing times the derivative of thing. That would be my formal mathematical language there. See, that is what we're doing in this case. Now, That's a polynomial, so I will put that first. So that would be 6x minus 4 times the secant squared of 3x squared minus 4x. Now, that's the best answer I can give. So you're looking at that and you're saying, well, I can factor this. You can factor a 2 out. That's not factoring, believe it or not. Factoring is when you write it as a product of things that can be set equal to 0. I can't set 2 equal to 0. It is absolutely correct to factor out the 2. It's completely unnecessary. Okay, my factor is 6x minus 4. If I factor out the 2, that doesn't change anything. That doesn't make it easier or harder to work with. So I just leave it like that. Should I factor the argument? No, I wouldn't factor the argument. I would leave it like that. So this is the best answer I can give in this context. Okay. Now, what if I have a function of a function of a function of a function? What if I keep going? What if it's deep? You know, I have f of g of h of q of p of x. Well, the chain rule says you just keep taking derivatives until you get to the innermost piece. So here's an example. I would like to take, let's say y equals the secant to the 4th power of 4x squared. Now you're looking at that and saying, well, actually, sorry, I don't need the parentheses yet. You're looking at that and saying, how is this a composition of a composition? Because that 4th power is outside the secant. In other words, this is the same as saying secant of 4x squared, which is already a composition. Secant's my function, and this is my innermost function, and I'm taking this whole thing and I'm raising it to the 4th power. So there's 3 deep. My outermost function is something to the 4th. My next function is secant, and my innermost function is 4x squared. So this would be f of g of h of x. Exactly. So, by the way, I don't need you to rewrite this, but you have to understand that's where the 4 goes. It's the outermost. So dy dx, I have thing to the 4th power. So this would be 4 thing cubed times the derivative of thing. But what's thing? Thing is secant x squared. But what's that? Well, I can put this 3 here. I know that. So I'm going to go ahead and write it there. Now I have secant of other thing. You can call it thing 1 and thing 2 if you want. Now I have secant of other thing. The derivative of that would be secant other thing, tangent other thing, and I still have to take the innermost derivative. Oh my gosh. Now, the derivative of this term I know is 8x. I already have a 4 in front, so I can make that 32x. I have a secant cubed. I have another secant. So that gives me secant to the 4th. I have a tangent. And I'm done. So that one was really lengthy. So again, I start with the outermost, boom, boom, to the 3rd power, and now I do the next thing. But the next thing is still a composition, so then I do the next thing. No way else to get this answer. So this is what chain rule is. Now that's not as common, right? To have 2 deep, but to raise a trig function to a power, that's not that big of a deal. That's a fairly simple concept. All right, let's try one. How about, I want to differentiate the cosine cubed of x.
Quick question, Professor.
Yes.
Would it be secant to the 3rd, or did you mean to put 4th? Oh, because that, all right.
Yeah, I'm putting those 2 together.
All right, thank you.
Yeah.
I was trying to figure it out and I was confused.
Yeah, I don't want that to be ambiguous. So I had a 3rd power plus and then another one. So that's what that got the 4th power.
Okay, thank you.
First one. Yeah, good question to ask. Yesterday, I think it was yesterday. I'm working a problem and I did something goofy, like I dropped an exponent or something. And then when the student said, Mr. Brown, I think you dropped an exponent. I went, oh God, yeah, it completely changed everything. So, oh, so glad you caught that. They thought I was going to be upset. Oh, I was thrilled because I would have wasted so much time and going, gee, why isn't this working? You know, I'm the only one that can't see it if there's a mistake because I'm standing, this close to the board. So how do I view this? Now, I don't need you to rewrite it, but how do you view this? You view this as cosine x, the quantity is being cubed. So I view this as thing cubed. This 3 is actually on the outside of the function. This 3 is not on the x. And by the way, this is huge. This is huge. And I've had people make this mistake recently. I'm cubing the cosine function. I'm cubing the argument. They're not even similar concepts. They would have nothing to do with each other. I don't think those graphs would even intersect, except maybe at one point. So I'm looking at that saying, I have thing to the third power. So the derivative is 3 thing to the second power. And I can put the 2 there times the derivative of thing. So now what is the derivative of the cosine function? We know that's negative sine. Now, whether you choose to put the sine second or the sine first is totally irrelevant. That's not going to affect anything, but it's negative sine. So my answer is going to be negative 3 times the square of the cosine times the sine. So that's my final answer. The order I write those is not important. There's no priority between sine and cosine. Okay, so I'm going to give you guys an exercise here, and I'm going to see if we can figure this one out on our own. Actually, I'll leave that up there for a moment. Here's the exercise. Giving you this function, I want to find dy dx. Do we know enough? So I'm going to pause for a moment. Come back. Let me go ahead and pin myself again if I can find it. Oh, I'm almost there. Oh, that's funny. It always takes me forever. The problem is I've got Nate now in my view. Nate, you are forever with us. Okay. It's the funniest thing is once I remove the pin from myself, it always takes me forever to pin. I don't know why I'm getting Nate pinned. There we go. All right. Negative exponent, it's got to go downstairs. Now, can I leave it as a 1/2 power? Absolutely. Absolutely, you could leave it as 1/2 power. But this is one of those times I would probably write it as a root because then it more resembles the original problem. And none of us have difficulty with that. If you wrote this quantity to the 1/2 power, that's exactly the same thing. So there's a couple of things I want you to notice. We could cancel the 1/2 and the 12. We could, and therefore we should. Also, we factored the chain rule factor. If you can factor it, you factor it, because now I can tell you where this equals 0 rather simply. This is probably the best version of the answer we could give. Now, it wasn't complicated, but when I looked at the original problem, I have to recognize, oh, it's a root. Let me change it to a fractional exponent. And now I just treat it like any other exponent. There's nothing clever about this answer anymore. Okay. Now, one of the questions that often comes up is root versus fractional exponent. When do you leave it? When do you change it? Does it ever matter? So the first rule is a root and a fractional exponent that are the same meaning. One is not considered better than the other. It's really a question of which one's more useful. Most of us, if it's a square root of something, we just write the square root. That doesn't trouble us. But does anybody here, my final answer were something like this. My final answer were x to the 7th inside the 4th root. Let's say that was my answer. Let's say that was a correct answer. That's often difficult to interpret, okay? that can be hard to interpret that thing. You say, well, I don't know what to do. And the other thing is, if I wanted to differentiate this, I can't differentiate it as stated. So the rule is, remember, the root is the denominator. So this would be x to the 7/4. And I think in every conceivable way, this quantity is way simpler to work with than this one. So if I was dealing with this, no, I would immediately change it to this. I'm not a big fan of things to powers under roots. I find them harder to read. So remember that the absolute is this. X to the a over b, b is the root, a is the power. That's the absolute rule that you learned hopefully in remedial algebra. So is there a rule in general? Does one better than the other? In general, I like this just because I have to change it to the fractional exponent anyway. Oh, by the way, if you're going to evaluate something on your calculator, you got to change it to the fractional exponent first anyway. The exception is if I have something like this, x to the 1 over n, that's the nth root of x. Okay, because x has been raised to the first power. When I have something in this form, that's generally when I'll write the root. So a 1/2 power, I'll write square root. 1/3 power, I'll write cube root. 1/4 power, I'll write fourth root because it's easy enough. It's when I got things to powers in roots, I don't like this because it's too easy for people to get it confused. So there's no absolute rule that says you must do one or the other. You do whichever one is more convenient and whichever one you feel more comfortable with. But it is always correct to leave things as fractional exponents. The only thing we say it's not simplified is if my exponent is negative. Oh, then I just got to throw it back into the denominator. That's the only thing there. All right, well, let's do another bad boy.
I have a quick question.
Sure.
As we're talking about exponents, I had one where it was like a root of, let's say, x to the root of a root of x to the 7. So it was root and then another root.
Were they both square roots?
No. Well, yes, they were.
So
they were within each other.
Something
And
like
that's
that?
where I get confused. Yeah.
Am I looking at that right there?
Yeah.
Oh, okay, well, let's do the inner one first. So what would this be? This would be x to the what power?
1 over 7.
Careful.
Oh.
7 over 2. X to the 7 stays x to the 7, but square root is half power. Are you okay with that? That's square root of x to the 7 is x to the 7 halves, and it's all inside a square root.
Okay.
Now, what do you do with, what's the rule now? What do I do with those guys? To a power? Multiply.
Adam?
Multiply.
Oh, multiply.
So that would be x to the 7/4, which is the equivalent of the fourth root of x to the 7th. Oh, square root of the square root is the fourth root. Yeah. If sometimes it helps to think numbers. Let's start with 16. What is the fourth root of 16? 2. What is the square root of the square root of 16? 2. So the fourth root is the square root of the square root. And why is it the square root of the square root? Because you multiply exponents at that point. Okay, this someone is just being mean and nasty. you don't ever run across the root of a root, but we do want to know how to deal with it. That's not something you're going to see a lot though. Okay.
Okay.
But yeah, if you can do that, absolutely, I would work with that. That's correct, but that's the one. Because what if I needed to take the derivative of this? I would first have to write it like this. That's a great bonus question, by the way. You just gave me food for thought there. Okay. Y equals, let's say, sine squared x times cos cubed x. Ooh. Now, I changed something on you here. I've got functions raised to power. So obviously there's chain rule going on, but I also have the product of functions raised to powers. So does that mean there's a product rule as well? Yes, actually the product rule takes precedence because I have thing times thing. So I definitely have to use product rule. So this problem here is a step above the previous problems. Now, I'm using the formal notation because I want you guys to get comfortable and used to it. The ddx and dydx and all these things, they typically take a little while to get used to, but you want to, after a while, everybody's conversant. It's like any other thing that you learn in math. Once you learn the symbolic notation, it's not bad. So let's write it out. It's the first times the derivative of the second plus the second times the derivative of the first. Okay, that's what the product rule states. Now, when I take this derivative, though, I have a function to a power. I have to use chain rule. When I take this derivative, I have function to a power. I have to do chain rule. So I now can say this is sine squared x times 3 cos squared x. I'm going to do it formally times the derivative of cos x. I'm finally to the inside there. Plus cos cubed x times 2 sine x to the first power times the derivative of sine x. Now, finally, we can be done here. So this is sine squared x times 3 cos squared x times negative sine x. Do put the parentheses, because if I don't put the parentheses, I am saying it's a subtraction, and it's definitely not a subtraction. And that would be cos x. Now we can put things together. So on the left term, I have a sine squared times a sine, that would be sine cubed, times cosine squared, with a coefficient of -3. On the second term, I have a single sine, and I'll have cosine to the fourth with a coefficient of 2. Now, is that the best answer I can possibly give? Can I factor this? I think I can factor this. What is common? I have sine to a power, cos to a power, sine to a power, cos to a power. Well, it looks like each term has sine to the first power at the very least. And each term has cosine squared to the very least. And what would that leave me with? -3 sine squared, and over here, plus cos squared. So the best answer I can give is the factored answer. Is there any trig identity I can employ here? Yeah, actually there are. I could use Pythagorean identities. For example, if I don't like cos squared, I could change that to 1 minus sine squared, and then I can combine things. The question is, does that make it easier? Does that make it more useful? I don't know. Depending on what you're doing, you may decide, you know what, I want my entire answer in terms of just sine or just cosine so that I can use Pythagorean identities. But that is a perfectly acceptable answer as is. So unless you have a reason to change using Pythagorean identities, I'd probably just leave it alone. So this one here was way beefier because I had functions to powers and I had to deal with those. Okay, so that's kind of the next thing we're going to look at. What happens in general when you have to use a product or a quotient rule and you have a chain rule going on at the same time? All right. Let me erase some of this. So what if, I'll just write it like this. I want to take the derivative of 3x squared minus 4 to the 6th power and 8x plus 3 to the, 8x plus 3 to the 4th power. All right. I want to take the derivative. And by the way, I really do need the outer brackets. If I don't have the outer brackets, I'm only taking the derivative, it appears, of the first term. I want to take the derivative of this entire product. A lot of folks don't like using parentheses, but remember, ddx is an operator. Okay, it's operating on whatever you say follows it. And so you put that thing within parentheses because what if you have a whole bunch of stuff, but you only want to differentiate the first of them? So this is good notation. So when I expand this, this is going to be first times the derivative of the second, which is still in brackets because I'm raising it to the fourth power, plus the second times the derivative of the first. Okay, we haven't actually done any calculus yet, but we've set ourselves up for what it is we're actually going to do. Now, when I differentiate that guy, this is going to be 4 times 8x plus 3 to the third power. Then what? Then times the derivative of 8x plus 3. And I'm going to go ahead and write it out formally. I'm going to show you that you can sometimes make this a little bit more efficient. Plus 8x plus 3 to the fourth, 6, 3x squared minus 4 to the fifth, and then times the derivative of 3x squared minus 4. I barely got that in. Okay. I'm still not done. I still have to take those derivatives. Yikes. So now at this point, I'm going to be lazy. I'm going to write, that's 8. I don't want to rewrite this entire quantity one more time. That's 6x. Okay, I got that. If I simply write the 8 and I write the 6x, then I will be completely finished with the calculus. But I'm still about a million miles from a final answer, because the final answer should be a product. It should not be a sum. If I wanted to graph this, if I wanted to analyze this, if I wanted to ask where does it equal 0, I have no idea in this form because I have a sum of a bunch of really big things. But if I factor this, which actually is not going to be hard, then I have an answer that I can actually manipulate. So when I'm looking at this, looks like I keep losing my exponent on this one. I don't know how I do that. There we go. We'll put that back in there. I have 3x squared minus 4 to a power. I have 8x plus 3 to a power in both sides. So the GCF, the greatest common factor, would be the smaller of the exponents for each thing. So I know that my answer is going to involve 3x squared minus 4 times 8x plus 3. I know it's going to involve that. The question is what exponents? So that's 6th power, that's 5th power. So the GCF would involve the 5th power. That's 3rd power, that's 4th power. So the GCF will involve the 3rd power. And now what will that leave me with? Well, I've got an 8 times a 4, that's 32. And 1 factor of 3x squared minus 4. 1 factor, because I've already got 5 of them here, or that one there, there's my 6. I already pulled all of this out. So I'm done with the left side. Plus. Now on the right side, I've got a 6 and I've got a 6x. I pulled out all of the 3x squared minus 4s, and I pulled out all but one of the 8x plus 3. So I have a single 8x plus 3. You notice the remaining terms here, each were to the first power, as they should, because these exponents differ by 1, these exponents differ by 1. So when I'm factoring out the GCF, I can't have exponents bigger than 1 inside there. Now, I'm almost done. I kind of need to clean this up. Okay, so let's clean that mess up. This would be 96x squared minus 128. And then here that would be plus 288x squared plus 108x. Put all that together, that gives me 384x squared plus 108x minus 128. Yikes. Now, is that factorable? Well, I know there's a constant in there that's factorable, but what about the quadratic? And here's the thing. This quadratic will have 2 solutions. There's no question I'm going to get 2 solutions. The question is, will my solutions be rational or will they be irrational? Because if my solutions are rational, that means it's factorable actually easily. If my solutions are irrational, then I would have to use the quadratic formula to find them. And in that case, I just leave it like this. So how can I know if it's rational or irrational. Let me grab a calculator. If I gave you a quadratic, okay, off to the side, give you a little bit of review here. I want to solve this guy. I know my quadratic formula. I know this, right? B squared minus 4ac over 2a. I know that. The b squared minus 4ac, that's called the discriminant. And there are absolute rules governing a quadratic. If the discriminant is negative, it means I get two complex numbers. I get imaginary stuff. If the discriminant is 0, then I have one repeated root. And if the discriminant is positive, then I get two real roots. But how do I know when my roots are rational versus irrational? If the discriminant is a perfect square, then I get two rational roots. If the discriminant is not a perfect square, then I get two irrational. I'd like to know if this is factorable or not without wasting a lot of time. These numbers are way too big. If I trial and error, I might be done, next month. So I'm going to find the discriminant. The discriminant is the b squared minus 4ac. This is actually something you should have learned in a remedial algebra class, but you may not have realized how useful this truly is. My Calc 2 class next day is going to be using this to do big, humongous calc problems. So let me do this on my calculator. 108 squared. 4 times 384 times 128. And I got some humongous number. Now I'm going to take its square root. And one of two things happens. Either I get an integer or I get a hideous decimal. I got a hideous decimal. That means this has two irrational roots. So I am not going to bother factoring it. If I do need to know where that quantity equals 0, then I would just use my quadratic formula. What if this was a perfect square? Then I would go ahead and factor this. But I'm not going to waste time trying to factor something that's not factorable. So the final answer I'm going to write, now, I can factor a constant out of this. There's no question I can factor a constant, but 4, I think, is the biggest constant I can factor out of it. So factor out the 4 or don't factor out the 4. It isn't going to make any difference in the long run. So I'm going to go ahead and write my final answer. Again, factoring out a constant is not factoring because the constant can't equal 0. So that's my final answer, and it's in the factored form. Now, there's a couple of observations you need to make here. Okay, this guy here and this part here. Notice in the original problem, my exponents were 6 and 4. Notice in my answer, my exponents are 5 and 3. That is not coincidental that they're each exactly 1 less. That came from derivatives. This stuff over here was all from chain rule factor stuff. I like to call this the chain rule junk. There's actually another name for it. In higher level, if you're an engineer, there's actually a cool name for this. It's often referred to as noise. No joke, it's called noise. It's not making any sound, but that's what it's often referred to. My final answer, if I didn't know anything about this, I could say my final answer, I know I'm going to have these guys to 1 less power and some stuff. Now, I couldn't tell you for the life of me what the stuff is. I actually have to go through, but my final answer agrees with now what it should have been, and that is looking at the exponents. So this is about as busy a problem as we have looked at. And there's nothing wrong. Every part of this was actually relatively simple. So let's do this, but a far more evil version of this. Okay, how do I do a more evil version of this? This was sufficiently evil for us. How about this one? Ooh, I want to take the derivative of a quotient where each term is being raised to a power. Absolutely, I can use quotient rule, but quotient rule will take me a lot longer than if I just simply rewrite this. Now, I mentioned last time, if you can simplify or change a problem and make it easier before you start, always do that. If my denominator is a trig function, for example, then you don't actually have a denominator, you just bring it up because the reciprocal of a trig function is another trig function. If your denominator is something raised to a power in general, I don't mean a polynomial that's raised to the first power. I mean something where I'm actually raising the entire denominator to a power, then it's absolutely without exception, always in every conceivable capacity, because I looked at every problem that possibly exists in the history of the world. I looked at them. I had some extra time last night. It is always easier to rewrite it. Oops, that's a 3, sorry. -3 with a negative exponent. Because these are the same problems. But I've just converted this problem into the one we just did. And I will save myself a significant amount of work in simplifying by doing this. If your denominator is something to a power, then rewrite it as a product, it will be easier. If your denominator is not being raised to a power, like a simple polynomial, you could rewrite it as to the negative first power, but you gain no advantage at that point. It's because this isn't a 1 that this is advantageous. So when we do this, let's go ahead and do it. But this time we're going to kind of speed up the process. So I'm going to say it and then I'm going to write it. So first times the derivative of the second. But let's just go ahead and actually take the derivative of the second rather than write d dx of the second and then do d dx. Let's just go ahead and differentiate it. Times the derivative of the second. Well, I bring down the exponent. I decrease the exponent by 1 times the derivative. Remember, you just did exponent thing to the exponent -1, and now I need derivative of thing. I'm going to write on here. There's my chain rule factor. Okay. Rather than writing the d dx, you can just differentiate. We write the d dx at first so we get used to the, kind of the algorithm that we're using. Plus the second times the derivative of the first. Well, let's see, I have thing to the 7th, so that'll be 7 thing to the 7 minus 1 times the derivative of thing. Now, believe it or not, folks, we are completely finished with the calculus. We just took the entire derivative. That is the derivative. First times derivative of second, second times derivative of first. What I don't have is a useful, workable answer yet, because I still need to factor out all the common factors. So I'm going to have a 6x plus 5 raised to a power, and I'm going to have 2x minus 3 raised to a power, and then I'm going to have a bunch of stuff, the junk. All right. I have a 7th power. I have a 6th power. The GCF would involve the 6th. And here's where we get into a little bit of trouble. I have a -5 and I have a -4. Anybody want to yell out which one do I use for the GCF? The -5 or the -4?
-4.
Which one's smaller? That's why this one gives us trouble. -5 is smaller than -4. Okay, so where is it? You got to go with the smaller. We chose 6 because it's smaller than 7. Remember, common factor has to be the smaller. But if I choose the -4, then I'm going to have an exponent of -1 over here, and that's not good. That don't work. All right, what does that leave me with? Well, here I have a -4 times a 2 and an entire factor of 6x plus 5. And a quick check, when I multiply these two, I get back my 7th power. I got that. Okay, cool. Plus. Now over here, I pulled out all the 6x plus 5s. These exponents differ by 1, but this one is 1 greater. So I have a 7 times 6 and exactly 1 factor of 2x minus 3. And again, I have 2x minus 3 to the -5th, 2x minus 3 to the 1st. There's my -4th. That's why I've got to pull out the smaller. Otherwise, I'd have exponents of -1, which again, that's not useful. That just makes things really hard. Well, this isn't so bad. So let's clean this up. So that would be negative 48x minus 40. That would be plus 84x minus 126. So that quantity there is 36x minus 166. Now, what about that term there? 6x plus 5 to the 6th power. And what about that term there? Because of the next negative exponent, I'm simply going to throw it downstairs to the positive 5th. And that's it. That's our complete final answer. And you notice it didn't take more steps than the last problem. Okay, if it took more steps, it was because I had to write this below, but I wrote that as I wrote the final answer. Now, can we justify the exponents on this one? Because it seems like that one decreased, but that one increased. Actually, no. Go back to this form. In this form, that decreased by 1 and that decreased by 1. But our representation is we must put the negative exponent downstairs. So it's still consistent with the previous example, okay, in how the exponents worked. So this one here, this isn't the worst. On the video, I've got a video posted for chain rule that hopefully you haven't watched already because it's examples of chain rule. After today, watch the video. I do a bunch of examples and I do one that's just so evil. I do a version of this, but with a square root and just, nastiness all over the place. But to show you that it doesn't really matter how the question is asked, you can still do it. And right now, we only have 7 functions that we can take a derivative of. 6 of them are trig functions. So I'm now going to introduce some formal mathematical notation that you will see in every textbook and every class, but we haven't done it before. So here's the thing. We're going to let u be a function of x. The universal substitution variable in calculus is we like using the letter u for whatever reason. We love u. We all love you. Okay. So we use the letter u, and a lot of times we do this as a shorthand notation. So if I said, I want you to differentiate x to a power, you know that's n x to the n minus 1. We proved that in class, certainly for integers. But what if I wanted you to differentiate u of x to a power? Well, this gets kind of beefy. Well, what we usually do is we just write it like this. To save ourselves time, we just write it like this. So now what's the answer to this question? Well, it's n u to the n minus 1. But this is a function of x, it's not an x. So the chain rule factor would be the derivative of this guy, which we usually write du dx, or you could say u prime of x. Both would be correct notations. This is the formal notation that we use mathematically. Now, this is the part that always troubles people at the beginning. We say d dx, we have function of x. If I throw a different letter of the alphabet in there, that doesn't cause problems. It means that that function is a function of that variable. That right there, the d dx, this says that I have one independent variable, and that independent variable is x. Another way of thinking about it is if you see any other letter of the alphabet, any other variable, it has to be a function of x. So if I said, take the derivative and a, b, c, d, e, if I'm differentiating with respect to x, it automatically implies those other letters are functions of x. So whether I write u of x or I write u, this statement right here says that that variable has to be a function of x. This would be the formal way of writing it. It just requires so many parentheses. So we have 7 rules right now. And I'm going to write them down. This is what you must know today. Whoops, sorry, that's a U. Oops. Run out of room real quick. And Okay, I'll get it in there, d dx. This is the formal way of asking the question. Now, what throws us, I'm asking you to take, for all 7 of these functions, I'm asking you to take the derivative with respect to x. That matters. You don't ever say, take the derivative of a function, because there's an infinite number of things I can take the derivative with respect to. Now, we get conditioned, we're using x and y because it's convenient. Okay, it's just easier to just stick with x and y, and we will. But there's not a single x in that statement. So it is implied that this u actually means u of x. It means function of x. This is just shorthand notation. Plus, that tells me that every variable that is not an x is a function of x. Why is that important? Because that automatically means there's a chain rule factor. So this is n u to the n minus 1 times the derivative of u, the chain rule factor. That is the formal formula that you will use forevermore. So what if this actually is an x? Then this would be a 1, like we said earlier, and that doesn't contradict anything. So let's keep going. So this would be then the cosine of u times du dx. This would be negative sine of u times du dx. This would be the secant squared of u times du dx. You see a common theme here. This would be the secant of u tangent of u times du dx. This would be the negative cosecant u cotan u times du dx. And the last one would be the negative of the square of the cosecant of u. Now we have about 14, 15 more functions we're going to learn derivatives of, believe it or not. We've got all of the inverse trigs, the hyperbolics, the exponentials, the logarithmic functions. We have a lot more transcendental functions. And every time we derive a new derivative formula, the very next thing we're going to do is give the chain rule version of that same formula, because that's the general way it will always be used. So again, if your argument is simply x, it means your chain rule factor is simply 1, and you don't bother writing times 1. That's redundant. But understand it's still there. So the rest of the time, there is always a chain rule factor. So if you look at the cover of any textbook, any calculus book, whatever book you're using, if you look at the cover, you will see all the derivative formulas, and all of them will have u's. You go, why do they have u's? Okay, somebody need to mute yourself. Why do they have
I had a
u's?
question. So what's the difference between with it being respect to x and the being u, or saying that it's going to be a substitution, versus say there's another factor in there, like say if there was say sine of u, but there was also an x, then would we only take the derivative with respect to x and then consider u as not a function of x?
If u is not a function of x, then the answer to every derivative question is 0. But you won't do that until Calc 3.
Okay.
If your other letter of the alphabet is not a function of x, then the answer to every, I'm not being sarcastic, the answer to every question is 0. It's equivalent to differentiating a constant. And that is something that becomes very important in Calc 3 when you introduce multiple independent variables. We don't do that in Calc 1 and 2. We do one independent variable. Therefore, any variable introduced in a problem has to be a function of the same independent variable. It's not possible to have multiple independent variables for the first 2 semesters. We not learn the math of that.
And so to ignore that problem, we're just assuming that u is automatically a function of x, just so it's not automatically 0. Right?
I think that's the point I've been making for the last little while.
Okay.
It cannot be anything else. There's no ambiguity whatsoever. Now, when you're writing the problem down, you don't have a u, you have stuff. So when we're differentiating, let's go back. I want to differentiate, how about the cube root of the tangent function? Ooh, that's good. Well, what's my u? In this case, your u is actually the tangent function, because you're doing the cube root of it. So you're doing u to the 1/3 power. But you're not making a substitution. Do not change variables. Some people will say, well, now let me make a whole change of variables. Let me write down. No. There is absolutely no such thing as substitution with a derivative. There is no such thing. You will never find that even on the worst YouTube videos. You will not find any human being doing a substitution with derivatives. Now, having said that, I will have a significant percentage of people turning in work where on every derivative they do a formal substitution. And to this day, I haven't the slightest idea where they got that because there's no textbook that does a substitution. I've never heard of a teacher doing it that way. Like I said, in Austin Powers, Dr. Evil, you guys all know him, right? He went to Evil Medical School. They actually say that, it's like somewhere in Belgium. I think there actually is a place called Evil Math School where people learn the evil math techniques that don't work. But even those guys don't do substitutions with derivatives. So never do a substitution with derivatives. And having said that, a third of all the answers on this quiz, I'm going to have people doing substitution of derivatives, which doesn't have any meaning mathematically. So I want to do this. I can't do this the way it's stated. That cube root is just really messing me up. So let's rewrite it as tan x. Let's write it like that. Okay, that makes it a little easier to interpret. I have thing to the 1/3 power. So according to my formula, this is of the form u to the n. Now, I'm not going to change it, but that's the form. This is my u, that's my n. So my answer should be 1/3 function to the -2/3. And then my, if you will, my du dx is the derivative of the argument. See, if the argument isn't just an x, then there is a chain rule factor, and it's that guy right there. So let's keep going. So this is 1/3 tan x to the -2/3 times the secant squared of x. Now, everything we said was correct. This is not the simplest version of the answer because I have a negative exponent, I got a fractional coefficient. So how can I write this cleanly? Well, first of all, I'll put it up here. It's a quotient. I'm going to have a tan x to the 2/3 power. And by the way, it is perfectly correct to put it under a root if you choose to. You can put it under the cube root as a tangent squared. That's absolutely correct. I wouldn't do it because I just think that makes it harder to interpret. But it is absolutely correct to change it to a root. I got that 3 going there. And then I got that secant squared up here. I would probably opt to leave it like that. Again, you could write this as tan squared x under the cube root. That's the same thing. I don't see that as being an advantage, but that's totally okay. But I want you to notice what I didn't do. I did not write this as tan 1/3 x, did I? And I did not write this with 2/3. The reason is the notation where we put a number here as the exponent only is defined for positive integer exponents. It is not defined for fractions. It is not defined for negative numbers. In fact, negative numbers mean something very, very different in that case. So if you are raising something to an integer power, a trig function to a positive integer, I'm raising something to the 4th power, I put the 4th there. But if I'm raising something to a fractional power, no, I've got to put the fraction on the outside here. Okay, you can't go there. There's no definition there. Okay, it'll get us in trouble if we try to. No, everybody would understand your intent. The problem is really when you have things like negative exponents. And I've already seen people try to do goofy things. You see, there's one thing you never do. You never raise a trig function to a negative power. You will never do that in your entire life because remember, the reciprocal of a trig function is another trig function. So you wouldn't raise a trig function to a negative power. You'd just have its reciprocal to the positive power. And here's one of the reasons that notation exists. See, we all agree on this. You don't ever have to do this. You could always do this. But what if I said I have 1 over the sine function? Would that be the equivalent of sine x quantity to the -1st? Would that be the same thing? Yes, it would. Would that be the same thing as just simply putting the -1 here? No, this is inverse sine, which is completely unrelated, not even a similar concept. Inverse and reciprocal are not the same, period. So, but I thought inverse and reciprocal are the same thing. No. Reciprocal means you go 1 over. The inverse of an exponential is a log, right? The inverse of a root is an exponent. They're not reciprocals. The inverse of a constant being multiplied is its reciprocal, because that's the definition of multiplication. That's the only time reciprocal and inverse are the same thing, is when you're talking about multiplying by a number. Oh, multiplying by 4 and multiplying by 1/4. 1/4 is the multiplicative inverse of 4, but all the other times inverse and reciprocal have nothing to do with each other. This is where people get in trouble. Okay, these are not even similar, reciprocal and inverse, but that -1 there means inverse. In fact, anytime you're using function notation, the -1 means inverse. It never in any conceivable context means reciprocal. Okay, so be mindful of that, so you don't do, you don't do crazy math, because we don't do crazy math here. Okay, I'm going to go ahead and stop now.